We'll begin by linking ellipses to real life. So we know that the path of the planets as they orbit the Sun are ellipses with the Sun at one focus. Now, if an object in space follows an elliptical path, we can predict the position of an object in space at a particular time. Now, an amazing property of the ellipse is as the light, radio or sound wave is emitted from one foci, it hits the elliptical surface and reflects onto the other foci. So you can see this foci emitting a wave and it reflects off the elliptical surface and back onto the other foci. Now, we've seen a real-life example of this, which is the famous Whispering Gallery, which is found in St. Paul's Cathedral in London. So if you stood at a particular point here and whisper, around you no one else can hear you. However, a distance away at another particular point, you can hear that whisper and nowhere else. Now, an ellipse is a set of all points such that the sum of distances from two foci, which are two fixed points, are constant. And what we'll now do is we'll try to visualize this definition of an ellipse using this video. So we have the two foci here, and these are two fixed points. We have the point P1 and P2, which are points that lie on the ellipse. Now, what we want to do is look at the distance of this point here to this first focus, which you can see is 6, and then this point, the same point P1 to the second focus, which you can see is 14. Now these two distances sum to 20, and we can do the same for this second point here. You can see that the distances from the foci sum to 20. Now in our example, we fixed this constant to a 20. Okay, so what we want to show you is what happens as these points P1 and P2 move around with the condition that the sum of their distances from the foci must be equal to 20. So let's have a look. So you can see it begins to trace out an ellipse. And if you just stop there, we can see that these distances indeed do sum to 20. And it doesn't matter where along the ellipse I go, those distances will remain constant. So we'll just complete it on the left-hand side. And that should hopefully give you a better idea of the definition of an ellipse. Now, looking at the equations of ellipses centered at the origin, there are in fact two types of equations in standard form. We have one for the horizontal ellipse and one for the vertical ellipse. Now, they look very similar, so how do we tell them apart? Well, here we have the x squared term being divided by a squared, and over here for the vertical ellipse, the y squared term is being divided by a squared. Now, in terms of numbers, if the x squared term has the bigger denominator, then the major axis is horizontal. If the y squared term has the bigger denominator, then the major axis is vertical. And it's important to know whether it's horizontal or vertical because it will affect the coordinates of key terms like the foci. Now let's look at a diagram of an ellipse. So what we have here is what we call the major axis, and we know this is horizontal, so this will be the standard form of the equation we'll be looking for. This is what we call the minor axis. In fact, these two are perpendicular to each other, and any ellipse has two axes of symmetry like we have here. Now the foci are always found on the major axis, and it has coordinates C0 and minus C0. Now if we look at this focus in particular, we can see the distance of this focus to the center of the ellipse is C units, and the distance from this focus to the center of the ellipse is C units. Now the two endpoints of the major axis are what we call vertices, and they have coordinates A0 and minus A0. Now if we want to work out the distance between these two, we can see that the distance between these two vertices is 2a. In fact, that's the length of the major axis, 2a units. So this agrees with what we have over here. Now, it's important to remember that the foci and vertices are always found on the major axis. Now, the endpoints of the minor axis are what we call covertices. They have coordinates 0b and 0 minus b. Now, if I look at this one, we can see it's b units away from the center. And if I look at this covertex, we can see it's b units away from the center. Now, another thing to remember is that the distance from a focus to either covertex is a units. So if I take this focus here, the distance between this focus and this co-vertex is a unit. The distance between these two is a units. The distance between these two is a units, and the distance between these two is a units. Now this will help us form a relationship between the values of a, b, and c. We can see b and c are perpendicular, so this forms a right angle triangle. So using Pythagoras' theorem, we can see that the values of a, b, and c are related by the equation a squared equals b squared plus c squared. Now, the length of the major axis is 2a, which we've seen for ourselves. And this equals the sum of the distances from the foci to any point on the ellipse. So if I look at this point on the ellipse, okay, and I can pick any point on the ellipse, the distances from the foci here, if I add these two distances together or sum them together, we get the value 2a. And I can pick any point on here, and the distances from the foci will always be equal to 2a. Now, for example 1, we are required to write an equation for an ellipse with vertices 0, -9 and 0, 9, and foci at 0, -7 and 0, 7. Now, these are two important bits of information. Now, we're not given a diagram, but I would always recommend you to draw a diagram where possible. So I'm going to plot these points in on our axes over here. And this tells us, you can see, that we're dealing with a vertical ellipse. Now, step 1 is we want to find the center, okay? And we can find the center by working out the midpoint of the two foci. So we can see the one focus here and the other focus here, and its midpoint would be 0, 0. Okay, now step 2, we want to find the value of a. Now, we know that the length of the major axis is 2a. Okay, so we can see here, this is our vertices in blue, and we want to know the distance between them, which will be the length of the axis, and we can see the distance between these two is 18. So if 2a equals 18, that tells us a must be equal to 9. Now for step 3, we want to find the value of b. We know that c equals 7. Why is that? Well, because these two foci we can see are 7 units away from the center of the ellipse. So now that we know a equals 9 and c equals 7, we can use this equation here and simply substitute these two values into this equation to give us the following. And if we solve for b squared, we get b squared equals 32. Now we can find out b by taking the square root of both sides. However, we know for the equation of an ellipse, we'll be wanting b squared. So I've left it as b squared. So step 4, we just write the equation, and we can do that by substituting the values of a equals 9 and b squared equals 32 into here to give us the following. And then we know 9 squared will simplify to give us 81. And this is the equation of the ellipse we're looking for. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below and send us a message now. Okay, with that said, let's get back to our lesson.
Now, we've looked at equations of ellipses centered at the origin 0, 0, and these are the two equations. If we look at the equations of ellipses centered at coordinates hk, so they're not centered at the origin, these are the two equations we have. Now, in fact, these two look very similar. We can see that the x squared has been replaced with x minus h, all squared, and the y squared has been replaced with y minus k, all squared. In fact, what we have here, these above equations, have simply been translated. H units right or left, k units up or down. Now, if we look at this example here, we can see an ellipse centered at the origin, and when we translate it, h units to the right and k units up, we can see that the size of the ellipse remains the same. The only thing that's happened is moved positions over here. So for example 2, we are required to write an equation for an ellipse with vertices at 6 minus 8 and 6, 4, and co-vertices at 3 minus 2 and 9 minus 2. Now, if you look at the vertices here, we can see that the x-coordinates are the same. If they're the same for the x-coordinates, then we know that the ellipse is vertical. And we can confirm this with a plot of these 2 points over here, the vertices and the co-vertices. We can see that the major axis there is vertical. Now, the center of the ellipse we can take as the midpoint of either the vertices or the co-vertices. So I'm going to use the midpoint or work out the midpoint of the vertices. So we know that the center HK can be worked out by simply adding the x values, so 6 plus 6, and then dividing by 2. Then adding the y values, so minus 8 plus 4, and dividing by 2. And this will simplify to give us the center 6 minus 2. Now, the length of the major axis is 2a. So we want this distance here. So we can see the distance between 4 and minus 8 will be 12. So if 2a, which is the length of the major axis, is equal to 12, then a must be equal to 6. Then the length of the minor axis we know is 2b. So let's look at this. So we can see the distance between these two here. If you look at the x values, 3 and 9, is 6. So if 2b is equal to 6, then we know that b is equal to 3. Now, we know it's a vertical ellipse. So we know this is the equation we'll be looking for, and we know that the a squared term belongs under the y squared term. So we can simply substitute h equals 6, k equals minus 2, a squared equals 36, and b squared equals 9 into this equation here to give us the equation that we're looking for. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. Now in example 3, we'll be applying our skills of writing an equation for an ellipse to a real-world problem. So what we have here in this question is that Mercury's greatest distance from the Sun, or known as the aphelion, is about 69.2 million kilometers away. Mercury's closest distance, or known as the perihelion, is about 45.9 million kilometers away. The diameter of the Sun is about 1.4 million kilometers. We want to use this information to determine an equation relating Mercury's elliptical orbit around the Sun in millions of kilometers. Now, before we begin to answer this question, we'll highlight some key information. So we can see that the aphelion is 69.2 million kilometers. So I'll put in our values there. We know that the perihelion is about 45.9 million kilometers. So we'll put that in our diagram here. And we know that the diameter of the Sun is 1.4 million kilometers from the question, and we can put that into our diagram as well. Now, looking at this diagram, we can see that these two positions of Mercury make the vertices of this ellipse. So what we can then do is work out the length of the major axis. And we can do that because we know that 2a would be equal to 45.9 plus 1.4 plus 69.2, which I've written over here. And this simplifies to give us 116.5. Now, if 2a is equal to 116.5, we know that a is equal to 58.25. Now, looking at the diagram, we can see that the Sun is not the center of the ellipse. The center of the ellipse is located here somewhere. In fact, we know the distance between this vertex and the center to be 58.25. We've just calculated this. Now, the Sun is in fact a focus point of this ellipse. So we want to work out the distance between this focus point and the center. So we call this the value C. Now, to work out what C is, we know this entire distance from the center will be 58.25. So we know A is equal to 58.25. We can calculate what C is. So C would be equal to 58.25, subtract 45.9, subtract 0.7. Okay. We don't want to subtract the whole of the diameter. We want to subtract half of the diameter, which is the radius, and half of 1.4 is 0.7, which is why we've done that there. When we simplify and calculate this, we get the answer C equals 11.65. Now that we know the value of A and we know the value of C, we know that the values of a, b and c are related by this equation. So we can simply substitute these two values of a and c into this equation here to give us the following, and then we'll try and solve for b squared. Now when we square these two terms, we get the following, and when we solve for b squared, we get b squared is equal to 3257.34. Because the major axis is horizontal, we know that the ellipse is horizontal. And also, because the center of the orbit is at the origin, then the equation relating Mercury's orbit to the Sun would take the following form. So now all we need to simply do is substitute our values of a and b into this equation to get the final equation we're looking for. So we have x squared all over a squared. So we'll square this term over here to give us 3393.0625 plus y squared over b squared. Now we know what b squared is. It's 3257.34 equals 1. And this is the final equation that we're looking for. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following. For example 4, we want to find the coordinates of the centre and foci and the lengths of the major and minor axes of an ellipse with the following equation. And then we want to graph this ellipse. So for step 1, we'll rewrite the equation in standard form. So what we'll do is the original equation that we have in the question, we'll reorder the terms so that the terms that have a variable x are together and the terms that have a variable y are together, and the constant term is on the right hand side. So we want the coefficient of x squared to be 1. So we'll take a factor of 25 out and factorize what we have in red here to give us the following. And again, we want y squared to have a coefficient of 1. So we'll take a factor of 9 out and factorize what we have here in blue to give us the following. The right hand side remains the same. Now that the coefficient of x squared and y squared are 1, we can apply the technique of completing the square. So if we apply it to this bracket in red here, we will get the following. And if we apply it to the bracket in blue here, we will get the following. And again, the right hand side remains the same. Now we multiply the square brackets for what we have here in red to give us the following. And we multiply the square brackets that we have here in blue to give us the following. And again, the right hand side remains the same. And the next step is to remove the constants minus 625 and minus 36 by adding 625 to both sides and adding 36 to both sides. On the left hand side, these two will cancel and these two will cancel. And on the right hand side, we'll be left with 225. The next step is to make sure that the number here is 1. So we'll divide both sides by 225 to give us the following. And then this is our equation in standard form for the ellipse. So now that we have the equation in standard form, we can find out the center of the ellipse. So we know that h will be equal to minus 5 and y is equal to 2 to give us the coordinates minus 5 and 2. So we can see that from here and there. Now for step 3, we want to find the lengths of the major and minor axes. So we can see that the largest denominator that we have here is 25. So this must mean a squared is equal to 25. Therefore, a equals 5, which means b squared must be equal to 9, and then b is equal to 3. Now, we want to find the length of the major axis, and we know this by working out 2a. So if a is 5, 2 multiplied by 5 is 10, and then the length of the minor axis is 2b, well b is 3, 2 multiplied by 3 gives me 6. Now, because this is a vertical ellipse, to find out the vertices, what we need to do is add 5 units, so a equals 5 units onto the y coordinate and subtract 5 units from the y coordinate. So if you do that, if we add 5 units to the y coordinate over here, we get the coordinates minus 5 and 7. If we subtract 5 units from the 2 over here, we get minus 5, minus 3. And for the co-vertices, what we want to do is add and subtract 3 units to the x coordinates here. So if you add 3 units to the x coordinate here, we get minus 2 and 2. If we subtract 3 units from this x coordinate here, we get minus 8 and 2. So for step 4, we want to work out the coordinates for the foci. Now, we know that the values of A, B, and C are related by this equation. We know the values of A and we know the value of B. So we can substitute into here to give us the following equation. So we know that A was 5, so 5 squared is 25. B was 3, 3 squared is 9. And we can solve for C squared to give us 16. And then C is equal to 4. Now, this is the center coordinate. What we want to do to find out the coordinates of the foci, we simply add or subtract 4 units to the y coordinate. So if we add 4 units to the y coordinate, over here we have -5 and 6. And then if we subtract 4 units from the y coordinate, we get -5 and -2. Now all that's left to answer the remainder of this question is step 5, which is to graph the ellipse. So we have all the information we actually need. So here's our graph. And in fact, we'll just plot in the vertices and the co-vertices, and then we can use this to draw in our ellipse. Now it's your turn to have a go at answering these questions. So pause the video before I reveal the answers. And the answers are the following.